All right, everybody. So now that welcome to geology. So now that we've done the three rock type videos, which ideally you've done by now, let's do what I didn't do in those, which I said would be part of that thing you should fill out. Is how would you tell the difference between them? If you went down to that cobble beach on campus, like between on the west side, right, between the health center and getting down to Bev's and Rudy's, and started just picking at rocks. How could you tell by looking at it which one is the other? And really, the short answer is, well, if you know what the three are, what would the minerals within that rock look like that are like a result of what they are? So this is a chance both to answer that question and to maybe just do a quick review on what the three types were. Why not, right? So let's start with, and this is going to be very quick. Like, don't expect this to be a substitute for the previous three videos. But if we have melts, this is going to create igneous rocks, right? Some work their way partially towards the surface. Some work their way all the way to the surface, in which case we give them names of extrusive igneous rocks and intrusive igneous rocks. Now, if you do the lakeshore thing, it's kind of one of those Oswego things you do. I'm not saying it's easy. There's ones down there that are like baffling. Why do we have such a great variety of rocks? I guess we should talk about that. It goes back to the glacial times. The glaciers acted like bulldozers that just embedded everything from where they came from, which is up to the north. So from the north, they picked up all of these rocks, brought them down, and just dumped them all when they melted back. Since then, 10,000-ish years of surface processes, rivers knocking them back out, shoreline processes dropping them out of those big drumlins, like the big bluffs you see at McIntyre Bluff at Sterling Nature Center or Chimney Bluff State Park or Fairhaven Beach State Park. 10,000 years of like processes where those get eroded away, but the bigger cobbles stay. And then they bang around on the beach and they get beat up and they get all rounded off. It's a long story to get us such a wondrous variety of rocks down there. And given all of that and given the like vast areas where they came from, sometimes some of them you pick up can be difficult to interpret. Some, though, you should be able to do. And honestly, because of the source region from where they come from, you're not going to find a ton of igneous around here. We tend to find more metamorphic and sedimentary because the areas to our north are more metamorphic and sedimentary. But sometimes you get lucky; you can find a couple. The intrusive igneous, you probably is your best bet. So, what things would you look for? Well, remember these have the larger crystals because they took time to cool down. These have those smaller crystals, the fine texture, or the porous ones, vesicular, or the glassy ones. Now, those, like a vesicular, like rock like pumice, a vesicular rock, isn't going to last very long, banging around on the shoreline, getting beat up by the ice every winter and all of that. You're very, very, very unlikely to find those. I did have a student find one once, and I'm assuming that it was actually like stolen from the lab and dumped down there because there's no way it would survive. If it's a wavy day down there, you can hear the cobbles all banging into each other, and it would just obliterate pumice in like an hour. Anyway, sorry, getting distracted. Those would be those types, right? So what do we look for within them that would be distinguished from the other ones? We could say that there are large, a little bigger for everybody. Maybe I'll write in red so it's a little more visible. Interlocking crystals. Or then we'll get into those other ones, vesicular, glassy, or fine. And this would be the hardest to see without any sort of blowing it up at all. Microscope. All right, so what do I mean by this? And I might even stick in there that they're uniform. I'll do that like here, like as a sub bullet. Uniform orientation. All right, so let's go in our heads to, we'll say that this box is melted rock. And as it begins to cool, in order of Bowen's reaction series that we mentioned there, you're going to start to form crystals of minerals. And this is happening like on an atomic scale. It's happening on a very, very, very small scale, which is why you really need long amounts of time to form coarse crystals. But what will happen is that any individual crystal within that is going to get bigger and bigger and bigger and bigger slowly through time as it cools off. So what I'm going to do is draw like just kind of a random blobby shape next to another random blobby shape next to another random blobby shape. And I'm just going to do this a bunch of times here while I talk. Picture, if you will, each one of these being a different mineral that slowly gets bigger and bigger and bigger and bigger until it's grown so much that it's interlocked with other crystals that are maybe simultaneously getting bigger and bigger and bigger and bigger as this thing cools from a liquid into a solid. Again, think of the ice cube as a similar but not perfect example. If we could zoom in and watch how an ice cube forms as that water goes from a liquid to a solid, you would see ice crystals getting bigger and bigger and bigger. And people that like study snowflakes, or you get real anal about the crystals you see within an ice cube, there's different ones that will happen based on how quickly they cool. It's kind of similar. These things grow and grow and grow and grow slowly until they're all interlocked with other ones. All right. So I guess I don't have images ready, which would have been the smart thing to do. Well, let's look at some granite. There you go. Google Images to the rescue. Interlocking crystals. Each one of these little bits, and this looks like it's probably from a countertop company, got bigger and bigger and bigger until they were all interlocked with other ones as they go. All right. Little piece of quartz there got bigger and bigger and bigger. Little piece of feldspar there got bigger and bigger and bigger. And now they all have interlocked with each other. And that's what I'm saying these interlocking crystals are. Now, the reason I chucked it uniform on there in the beginning is because you can get some of this with metamorphic rocks that have gone under all that heat and pressure. But as we'll see in a minute, those are going to have like a more preferential alignment, preferential direction. Vesicular, I guess we should just add to it right here. Has the gas pockets. That's the definition of it, like Swiss cheese, little holes in it. Glassy is glassy. Looks like a hunk of glass. All right. Take any of the pre-existing rocks and put them on the surface of the earth, and the dynamic atmosphere and the water cycle are going to beat up on those rocks, as well as plant and animal life beating up on those rocks. It's called weathering. So we would have weathering makes smaller rocks, which we'll call sediment. Those pieces of sediment then will enter streams and rivers and work their way downstream, breaking away from their deposits, flowing in the water, either bouncing along the bottom or being suspended in it, or as we learned, even as on a molecular level, as dissolved materials where ions are being transported downstream. So, transport of those is what we tend to refer to as erosion. But it can't go on forever. Eventually, this stuff's going to land somewhere, particularly where the water slows down, which tends to be when it makes it to larger bodies of water. So let's do, it gets out to larger bodies of water, it starts to settle, and you're going to get layer upon layer upon layer upon layer of sediments dropping down towards the bottom. Excusing my inability to draw well. Lower in that, as more and more piles, that's that whole process of lithification. Let's check that vocab word on there. Shouldn't be new news. This should be like from the sedimentary section that you already did. That happens down towards the bottom of the water, gets squeezed out. The mineral sense within that will cement together those particles. Now, some things to note. Larger particles need more energy to move them along. Smaller, very fine particles don't need much. So running water acts as a natural sorting mechanism. And an easy experiment to do with that is to go down to the beach, look at the rocks. In any one section, they're all about the same size. And where's all the sand? It's all gone. The running water of the waves and the winds is a fantastic. It looks like chaos. If you're there on a choppy day, it's going to feel chaotic, but it's actually like relentless organizing. It's taking everything small and washing it out to take somewhere else, and taking everything large and leaving it there, and everywhere in between, giving you nice organized piles. The broad pattern is that we would get larger sediments near shore and finer sediments offshore. So when you find a rock, if you find a sandstone and you find a shale, and you know that this one's made out of sand and this one's made out of mud, and you understand this principle, you can backwards go back, and here's some sandstone right here. You can go backward and say, okay, I know what environment sand tends to land in. I've been to a beach. This is that preserved. I know what areas that the finer sediments tend to settle in, way offshore. This is what I'm holding when I'm holding a piece of shale. All right, so what do we look for if you had to identify that? Well, it seems maybe like this is sorry about that, feeling a little sick. It may seem this is like almost insulting to say, but what do you look for in sedimentary rock? You look for sediments. I mean, if I handed this to you, you would be able to feel the sand in this. I do this for a minute and there's sand all over my desk. Are there sediments that are visible? Can you see cemented particles of some type? Conglomerate would be a good one for that. Let's rely on Google Images again. I mean, a no doubter. Here's different bits of sediment, even though we got some larger size in here, some larger pebbles to small cobbles surrounded by this kind of sandy matrix that's cemented particles, things that have been cemented together. The huge giveaway, the easiest one out of this whole entire list, is going to be what if I see fossils? You see fossils, job done. It's sedimentary. Fossils form when animals land in water and get buried by sediments. So there you go. Job done. You got it. Now the evaporites can be a little bit trickier, but we're going to stick with, I mean, any questions I would give you on the test wouldn't be the harder end of each one of these. It'd be, what are the big distinguishing things you could see on a rock to say that this is the one, this is where it belongs. The drawing I usually do down here, as lame as it may be, is I draw a bunch of circles. So if you're opting to do these notes, this is just kind of a visual idea that we take a bunch of different bits and we put some pressure on them, certainly not metamorphic pressure like we're about to talk about, some pressure, and cement those bits together. You got yourself sedimentary. Commonly, because sediments tend to land in layers and layer upon layer upon layer. In fact, in this one, you may barely be able to make out some, a little bit right over here. Some slight layers of pink within the white. You get layered sediments. Cool. All right, we'll move on to metamorphic and get you out of here. All right, our rock cycle diagram down here doesn't really leave us with the depth we would need for metamorphic, but we could say, hey, what if we're kind of compressing information here? So I'll draw an arrow with like a break in it to say that like we're talking here at depth. You can't do a scale model on one piece of paper, not very easy. At depth, you get enough heat and pressure which sparks minerals, even creating new minerals from whatever was in there at the time that it formed. So you're going to look for distorted minerals, right? You're going to look for, if I'm looking for a metamorphic rock, which is rock that has changed due to heat and pressure, I'm going to look for signs that the minerals within that have changed due to that heat and pressure. So the big one, which is kind of throwing a new term at you, not that we didn't mention it in the video, is the foliation. I could also throw mineral alignments. Make granite nice, and that's the most apparent form of foliation. It's called banding. They're like no brainer to see. And when they're all aligned up like that, and I know that might look like a sedimentary layer, but there's a difference. That's a sign of that pressure that smushed all those minerals into those bands. Let me look one other rock. Schist, like harder to see, but within the way that the mica, the mineral that makes these bits up, all line up, we can call that a foliation as well. So you look for these foliations, you look for mineral alignments. Banding's a dead giveaway. It's an easy form of foliation to see. And why? The why is that extraordinary amounts of heat and pressure, not just what it took here, but extraordinary amounts of heat and pressure will take a rock and basically smash it flat, alter the minerals within it, even creating new ones until they're all lined up perpendicular to that pressure. What do you think? Sound good? So there's your basic differences on the three. Hope that makes sense. Shoot me an email with any questions. We'll talk to everybody soon.